Welcome to the reactions of alcohols. So in this chapter, we're going to talk about the type of alcohol reactions. We've already talked about the synthesis of alcohol in our previous lectures. And in the synthesis, we also included oxidation reduction. So I am not going to be redundant, but reduction is a way to make alcohols, and oxidation is a reaction of alcohols that is in this category. So you'll need to go back through and review those reagents and the charts of oxidation and reduction. Alcohols can undergo dehydration to an alkene. So if you have an alcohol such as this, and you react it with sulfuric acid, and this is review, you get protonation of the OH, because you know that the OH is a horrible leaving group. So you get protonation. Now that's water, and water is an excellent leaving group. Okay, so water is an excellent leaving group, and then you basically have this is your alpha. So when we're doing elimination, dehydration to an alkene is elimination. This is under acidic conditions, so this is E1. So this will leave, and then you get a secondary carbocation. You do your carbocation test. If you switch places here with a hydride, it's still secondary. Here's a primary, so that is as stable as it gets, so you can just leave it. And then another molecule of water will come in here and deprotonate, and then you get an alkene. And the majority would be trans, because trans would be thermodynamically more stable, which is Zaitsev's rule. Okay, so the reactions for reactions of alcohol are dehydration of alkenes, that's review, oxidation of alcohols, so that's, we talked about that last Pogel exercise. And so an oxidizing reagent here, if you wanted to go just to an aldehyde, then so 1, 2, 3, 1, 2, 3, this is a primary alcohol. PCC, usually you do this in dichloromethane because you don't want water around, and you have an aldehyde. If you wanted this primary alcohol to be oxidized all the way to a carboxylic acid, you'd need to use something like the Jones reagent or the Swern, which is also in your slides. Jones here is Na2, Cr2O7, and sulfuric acid. So there's water around, and in that case you have a carboxylic acid. So each one of these should be added to your reagents sheet. And then you have tertiary, not tertiary, secondary alcohols. So if you have a secondary alcohol here, so there's your carbon connected to 2 carbons, and you can use PCC or you could use Jones, it won't matter, because the highest oxidation is that these reagents could undergo for a secondary is a ketone. Tertiary alcohols, there's no hydrogen, there's no like alpha hydrogen, so no oxidation. So there's no hydrogen on that carbon. So that's oxidation of alcohols. The other reactions of alcohols is substitution to form alkyl halides. So we'll go over that, and then we'll go over reduction to form an alkane. So I'll show you that reaction. So that's a reduction to form an alkane. We also have esterification, tosylation, and tosylation you'll see is linked with the reduction to form an alkane. You have to do tosylation first, and then Williamson ether synthesis. Okay, so I will give a brief overview of those reactions, and then we'll work your POGL activity 16A on this lecture section. So, substitution to form an alkyl halide. If you have an alcohol, so let's do this first one here. Okay, so if you have an alcohol, and you react this alcohol with like HBr, okay, that's acid. So the first thing that's going to happen is the alcohol is going to get protonated, just like we saw in the sulfuric acid. So now you have a great leaving group, and then you have the bromide, which is a good nucleophile. And so this can do reactions such as this, and that's how you can get a substitution. This would be an SN2 reaction. Now, this water is a good leaving group. This is this would be SN2 if you had a tertiary or a secondary alcohol. This reaction would be an SN1. And so let's look at what that would look like real quick. So nice little review here of the, let's say here we have a secondary. So this is secondary alcohol, and we're reacting it with HBr. You're going to get protonation, because OH is a horrible leaving group. And now this is a great leaving group, and this is going to leave first. So we've got to do stepwise mechanism. So the leaving group leaves, and then is this your most stable carbocation? Yes, right? And then the bromide will come in as your nucleophile in step number 2, and there is your alkyl halide. If you react this with HCl, so we're making alkyl halides from alcohols. And the problem with HCl, so if you wanted to do this with HCl, you're going to get no reaction. It's because the chloride is a weaker nucleophile than the bromide. It's small, it's less polarizable. So you can do a Lucas, because Dr. Lucas figured this out, a Lucas reagent, which is just adding some zinc chloride. And the zinc will activate the HCl. So if you use zinc chloride and concentrated HCl, then tertiary alcohols will react in 1 minute. Secondary alcohols will react in about 5 minutes, and then primary not at all. So even Lucas reagent will not work with primary alcohols. And basically the mechanism here, so we'll look at a tertiary alcohol. So if you have a tertiary alcohol, okay, and you add the zinc chloride, the zinc is a Lewis acid, so it will accept these electrons from oxygen, and that's what a Lewis acid does. And what happens then, it forms a complex, like an acid-base reaction with the zinc. And then this helps pull this to leave. So now you have your leaving group, and it's a great leaving group. And you get a carbocation. And that's a tertiary alcohol. So this is a tertiary carbocation. And so now the chloride is strong enough to act as a nucleophile because that is a full carbocation. And so that's why tertiary alcohols will react in 1 minute, and secondaries will react also by SN1. So tertiary and secondary alcohols will react by an SN1 mechanism because you're getting a carbocation. Now, limitations of the HX reaction. So these are limitations of HX. So that means HBr and HCl to make alkyl halides. You get poor yields. Okay, and you also have competition with elimination reaction. So if you can avoid this reaction, these mechanisms, if you can avoid these reagents, then do. Okay, and I'm going to tell you how to avoid it. So I'm going to give you, I'm going to tell you to use phosphorus halides. And so let's look at those reactions. Okay, so we're still making alkyl halides from alcohols. And I'm telling you to use phosphorus halides. So you get good yields with primary and secondary alcohols. Okay, so if you want to make an alkyl chloride, the reagent you want to use is phosphorus trichloride. Okay, or better yet, I'll put it in green, you should use thionyl chloride. This is called thionyl chloride. Okay, so this is for primary and secondary alkyl chlorides. If you want to make an alkyl bromide, you should use phosphorus tribromide. Okay, and if you want to make an alkyl iodide, so I would add this to your reagent table, you'll want to use phosphorus, and then you need to add iodide. And what this does is in situ, and what in situ means, it does this in the reaction. It'll make your PI3 reagent. PI3 is not stable, so we can, at room temperature, so we can't put this in a container. Thionyl chloride, you can actually have a bottle of this in your reagent. PBr3 you can have, and PCl3 you can have this in a reagent bottle. And the yields are all good. I mean, if you look in your slides, you'll see yields of 85%, 90%. Okay, let's go through a mechanism. So if we have an alcohol, and we treat this with PBr3. So I'll do one. Phosphorus loves oxygen, okay? And so does aluminum. So these, but phosphorus will, phosphorus has an extended octet, and so it really likes 5 bonds, okay? But sometimes you'll see phosphorus with 3 bonds. And when phosphorus has 3 bonds, it basically has these empty orbitals. And so that is great for oxygen because then oxygen can go and dump its electrons into phosphorus. And when it does this, then phosphorus can have its 5 bonds that it wants to have. So you're looking at phosphorus, or it doesn't get 5 bonds yet, and then the bromine leaves. Okay, so phosphorus has 3 bonds here and 1 lone pair. And so still it has 3 bonds and 1 lone pair. And then the bromide is here, that left. So we'll just make this red. And the bromide's here and it left. And now that has a full negative charge. And what you've done is you've activated this. This is an excellent leaving group. So it's kind of like that zinc chloride, but now we've converted the horrible leaving group, OH, into an O phosphorus leaving group. And so now we have an SN2 reaction. So this is an SN2 because bromide's a great nucleophile, and you get this. So you're also going to get inversion of stereochemistry. So if you have this alcohol coming at you, then the bromide is going to go away from you. So because it's a backside SN2 attack. So keep in mind you do have stereochemistry there. Now thionyl chloride, you don't have stereochemistry. You actually have more of a retention of stereochemistry. The mechanism is still somewhat controversial. So if you have thionyl chloride, and this is what thionyl chloride looks like. So this would be your reagent of choice for your alkyl chloride. This comes here, up, and leaves, but it doesn't totally leave. And so it's kind of a weird one here. We reform the, you see how I did this double-headed? That's if you want to save time. The chloride actually kind of hangs around. So I don't know if it's like an intramolecular, but usually we don't even put stereochemistry here because you get this thing called an ion pair. And part of it might even be this ion pair is somewhat like this. So so you don't have to worry about stereochemistry. No worries on stereochemistry with thionyl chloride. Okay, so that is how you would want to make your alkyl halides from the alcohol. Okay, so we've talked about dehydration, we've talked about oxidation, we've talked about converting alcohols to alkyl halides using the phosphorus reagents. So we're looking at PCl3, but better than PCl3, I would use thionyl chloride to make an alkyl chloride, and then PBr3 to make an alkyl bromide. This is what's commonly used. And then phosphorus and iodide to make an alkyl iodide. Okay, so we've talked about that. The theme here is alcohol, the OH, is a horrible leaving group. So we've reacted with acid to make it a better leaving group. So the other reactions you're going to do is you're going to do reduction of the alcohol to an alkane, and then this is going to be done together with a tosylation reaction. So let's look at that together, and then we'll work Pogles to reinforce these topics, but this is kind of more of a summary. So if you have a secondary alcohol here, and you want to make a tosylate, then you do Thionyl Chloride, and you usually use a little pyridine. And let's use some stereochemistry here. Now, Thionyl Chloride, what does Thionyl Chloride look like? Well, it's toluene connected to a sulfonyl group. Now, this is like the world's best leaving group. Pyridine is just a little bit of base. It's called a proton sponge. And so what happens here is this will come here, and this comes up and comes down, and then the chloride leaves, and you actually convert you could put it like this. This is your tosylate. Now it's not totally done yet because the proton sponge will make this neutral by coming here and taking the deprotonation, and then you get pyridinium chloride, which you all saw that is part of PCC, and then you have a tosylate. You can write O-tosyl like that, or you can draw the structure, which is the tosylate out. Now, also note that the stereo center has not been inverted. See, we have retention. This is called retention of stereochemistry because we have not touched that sp3 carbon center. We have not touched that carbon. So we retain the stereochemistry. Now, tosylates are nice because they're not done under acidic conditions. So this is not acidic. It's not even really that basic because pyridine, somewhat basic, but it's really more of a proton sponge. These are anhydrous conditions. So now we've converted, the power of this is we've made a tosylate. We've converted this horrible leaving group into a great leaving group, and we didn't have to use any kind of acid. Okay, so now reduction of alcohol. So we can take this and put it in a solution with lithium aluminum hydride. So if you put this in a solution of lithium aluminum hydride, and so you've been familiar with that reagent, okay, that delivers a hydride. So if you want to just write a hydride, then the hydride is going to do an SN2. And now you have the hydrogen there, but that's the same thing as an alkane. So that's how you reduce 1, 2, 3, 4, 5 pentane, an alcohol. So this is an alcohol to its alkane by first making a tosylate and then reacting with lithium aluminum hydride. Okay, the other reaction that I'd like to illustrate here is the Williamson ether synthesis. And this goes through an alkoxide. So we're going to have to convert the alcohol to an alkoxide. and then you're just doing an SN2 reaction to make an ether. If you want to add that to your reaction sheet. So let's look at something like this here, our secondary alcohol. And we've talked about this, so this is review. To make an alkoxide, you just use sodium metal, or you could use sodium hydride. And both of these make hydrogen gas that just goes away, which is nice. And it's really an acid-base chemistry reaction. And so there's your alkoxide. And so once you make your alkoxide, if you react this with a primary, you have to react it for Williamson ether synthesis, you have to react it with a primary alkyl halide and do an SN2 reaction. You don't do it with a secondary because you're going to get elimination. This will act as a base. So if you have an alkyl halide, so something like this, okay, so then you can do an SN2, and that answer then becomes 1, 2, 3, 1, 2, 3. And that's the Williamson ether synthesis. You see that that's an ether. And so you go through forming an alkoxide, and we've learned about alkoxide. The only other reaction in your Chapter 11, Reaction of Alcohols, is esterification. And there's also a POGIL exercise on that, but we'll go ahead and show you that. So this is called the Fischer esterification reaction. And so it's going to make esters. So if we take like an alcohol here, and we react it, this is an equilibrium. So we react it with a carboxylic acid, so you need an alcohol, a carboxylic acid, and then you have to add sulfuric acid. You will get an ester. And so I will make the ester portion in red. So this alcohol becomes the ester portion. And this is your carboxylic acid, this is your alcohol, and this is your sulfuric acid. Now, in order to drive this reaction forward, because you never want a reaction that's equal, okay, you have to do Le Chatelier's principle. Okay, so you basically do an excess of alcohol. Okay, and that's going to push it forward to the product. And then sometimes you will use a thing called Dean-Stark trap. And it will trap water, because you also get water. Okay, and so if you pull the water off, it will pull this reaction forward. So what does the mechanism look like? Well, let's look at the mechanism. The mechanism here, the sulfuric acid will actually protonate the carbonyl. And this makes it even more nucleophilic, because if you did your resonance structure here, you would see that you could do resonance structures there. Then your OH here will attack the carbonyl. And then you get, I think I drew that right. And then you got sulfuric acid. One of these OHs have to leave, okay? So this is really a hard reaction to drive forward, because why would one leave over the other? And the reason why you keep pushing it until you get your ester formed. Okay, so then now these electrons collapse and push this. This is your leaving group. And you see that you have thing like this, and then water. So you lost your water here. There's your water that you lost. And that's what you have to trap to drive this reaction forward. And then you're going to get sulfuric acid has water in it. So that's a lot of times what we'll do when we want to draw this mechanism. And now you have your ester. A lot of times you do that in organic chemistry lab. Fischer esterification. Esters typically are your perfumes. They smell really nice, and you get a lot of esters in your fruits, and your fruits smell really nice. So that's a Fischer esterification of converting alcohols into esters. Now at this point, let's work your POGL activity 16A. So for POGL activity 16A, we're going to look at how alcohols can act as acid, bases, nucleophiles, and electrophiles. So let's do Model 1, and this is a review of acid and base reactions. And we have an equilibrium arrow there. All right, so let's read 1A, or just 1. Label the conjugate acid and the conjugate base in the general reaction shown above. Okay, so your acid and base are on the reactant side, and your acid has the acidic proton. The conjugate acid and the conjugate base are on the product side, and the conjugate acid is going to have your hydrogen, the proton that got transferred, so then the other is the conjugate base. Okay, 2. We're going to look at the acid-base reaction in terms of proton transfer. The acid loses a proton. The base, see the B, gains a proton. The acid-base definition refers to the gain or loss of a proton. Did you say Bronsted-Lowry? Definition. So this is review. 3. Consider the acid-base reaction in terms of electron pair transfer. The acid accepts the electron pair. The base will be donating, so it donates this electron pair. And this is the Lewis definition. Describe the differences between the two. Well, Bronsted-Lowry does acid-base reaction in terms of proton transfer, where Lewis is a transfer of electron pair. Look at the curved arrows. Recall that the curved arrows show electron flow. Which acid-base definition illustrates concepts of curved arrows? And that would be, I don't care what you say, but I guess it would be more of a Lewis, because you're talking about the electron flows where the base is donating an electron pair and the acid is giving up its electron pair. Accepting electron pair. Okay, C. Predict the products in the following acid-base reaction. Label each as acid, base, conjugate base, and do the electron pair movement. Okay, so now we're going to actually use real reagents here. So we're going to do the HBr plus OH. And then the product here is water plus Br minus. I don't like to do equilibrium arrows because I want you to do the real ones, so you can fix that. Here's your acidic proton, so this is going to be your acid. What's the pKa? It's probably about -10, so less than 0. These are inorganic acids. They're a lot more acidic than your organic acids. Okay, so this is your base. You notice I put on my electron pairs. So this is going to take the proton, donate it to bromine. So now you got bromide over here, which is your conjugate base. This is your conjugate acid, because here's your hydrogen. And now you got to assign a pKa value to water, 15.7. So it's definitely going to go towards the product. And that's how you should do all your acid-base reactions. Okay, that's a review, and that shows you how of acid-base reactions. Now we're going to do Model 2, where alcohol can either be an acid or a base. Okay, so Model 2. This is where alcohols can act as an acid or a base. So it depends on what it's paired up with. What do you put in the reaction vial? The R can be any carbon component. Equation 1. Equation 2. And then we'll review pKa values. So a strong acid has a pKa of less than 5. A strong base have a pKa of greater than 30. And alcohols have a pKa of 15, which I always say 16 to 18 to be exact. Alcohols have pKa's from 16 to 18. So you might as well just do that. Okay, consider the review information about pKa values in Model 2. For each of the following pKa values, determine if the compound would be a strong acid, strong base, or neither. So pKa of 4, strong acid. pKa 45, strong base. pKa -5, these are your inorganic acids, strong acid. pKa of 20. Did you write neither? Yes, neither. Okay, question number 6. What is the approximate pKa of alcohol? And I would say 16 to 18. Based on this pKa, an alcohol would act as a what? Strong acid, strong base, or neither? Neither. Okay, so if you want to explain that, an alcohol could donate a proton or it can accept a proton. So it can donate or accept depending on what reagent it is coupled with in the reaction. Okay, so now let's answer question 7. For the reaction in Model 2, label each species as either acid, base, conjugate acid, or conjugate base. Each species should have one label. Okay, so for equation 1, what role does the alcohol play? So here, this is your alcohol, and your alcohol is actually taking that proton. So there's your acidic proton. So this is going to be your acid. This is going to be your base. And here's your proton. So this is your conjugate acid. And so in the equation 1, the alcohol acts as a base. For equation 2, what role does the alcohol? Well, let's find our acidic proton. And here's our base. And those electron pairs go and take that hydrogen. So here it is here. There's our acidic proton. So this would be our conjugate acid. This is our acid. And then the RO is now here, which is a conjugate base. And that would be your conjugate base over here. So, acid. 8. In Model 2, draw curved arrows to indicate electron flow. And we did that. Okay. Okay, number 9. Draw the products of the following reaction and identify each species as either an acid, base, conjugate acid, or conjugate base. Okay, so let's work number 9. And what is this a Lewis structure of? I like to put in my lone pairs. You know, oxygen has 2 bonds and 2 lone pairs. And I'm not going to put my equilibrium arrows in because I like to compare my pK values and figure out should I use big or small. Okay, so let's find our acidic proton. So which proton is being transferred? It's going to be this one. Okay, and then these lone pairs from this is your alcohol, and this is sulfuric acid. You've seen it as H2SO4. So if you put alcohol and sulfuric acid, it's going to take that proton. So there's your curved arrows. So this is your acid. This is your base. And then over here, the proton went here. This is your conjugate acid. This would be your conjugate base. And we assign pKa values to acids and conjugate acids. pKa is like -10 for sulfuric acid. pKa of your alcohol, 16 to 18. So majorly towards the product. So there's your conjugate acid, conjugate base. Okay, number 10. Question number 10. Once your group has reached an agreement on the questions, determine under what conditions an alcohol will act as a base and what conditions it will act as an acid. Okay, so what did you write? Alcohol will act as an acid when it is in the presence of a strong base. So what would you say when it will act as a base? So alcohol will act as a base when it is in the presence of a strong acid. And that could be H3O plus, and this could be sodium hydroxide. H3O plus, you know what that pKa value is? I think it's like -1.7. So that's a strong acid. Okay, it looks like we have one more model, and then you are welcome to do your additional problems. So now we're doing Model 3, and this is a review of nucleophiles and electrophiles. And so why do I do the nucleophiles here? Because nucleophiles have lone pairs, negative charge, or the alkenes have pi bonds. Electrophiles have positive charges, or they have unhybridized p orbitals that are empty, inviting lone pairs. Electrophile, and here we have a nucleophile. E nu. So you see how forms a bond here. Those electrons go here. And this is the way you should always draw your electron flow arrows. So review information. Nucleophiles have either a negative charge or lone pair of electrons. And electrophiles have either a positive charge or a good leaving group. So let's answer question 11. A. Consider the general reaction between a nucleophile and electrophile shown in Model 3. A nucleophile donates the electrons. Okay, so it's going to donate an electron pair. B. An electrophile will accept these electron pairs. C. Compare the reaction in Model 3 to reaction in Model 1. What is the same between a nucleophile and a base, and what's the difference? Okay, a nucleophile is a base when it accepts a proton. A nucleophile, because a base will donate electrons to the proton. A nucleophile will donate its electron pair to carbon. So if it donates its electron pair to carbon, it's a nucleophile. It acts as a base when it donates its electron pair to proton. So that's the similarities and difference. They're both donating an electron pair, but a base donates it to proton, a nucleophile donates it to carbon. Okay, what is 12A? Circle the compounds that are capable of acting as nucleophiles. So did you circle the ones with a negative charge and a lone pair? This is another reason why you put in your lone pairs. So did you circle those two compounds, the hydroxide and the ethanol? Okay, look at the next one. 12B. Now you want to find the ones that electrophile. Well, electrophiles have a positive charge. So this is an sp2 carbon, so it has an unhybridized p orbital. And there you go. And that has a leaving group. The following reaction when alcohol replaces a halogen. So let's do questions number 13 and 14. So step 1. And you are doing this reaction in methanol. Step 3. All right, so 13A. In step 1, which bond is broken? The sp3 carbon-bromine bond is broken. Draw curved arrows on the scheme above to show step 1. So we showed step 1. What about B? What is the role of the alkyl halide, nucleophile or electrophile? This would be the electrophile. Does this agree with your definition on 11? Yes, it well, you could say this is your electrophile because the carbocation now is going to accept a lone pair. And this is your nucleophile. So once the leaving group leaves, you have a carbocation. Okay, so what about draw curved arrows to show the electron flow movement? So we just did this with the nucleophile attacking the electrophile, the carbocation. Okay, 13D. What is the role of the alcohol in step 2? So in step 2, it's a nucleophile. Does this agree with your definition? Yes, nucleophiles donate an electron pair. Okay, 13E. Step 3, which bond is broken? So here's step 3. And basically you're going to have to get another molecule of alcohol to come and take that proton for step 3. And what bond is broken? It's the OH bond. We call this a proton transfer. Deprotonation. So draw curved arrows to show this electron movement. It's called deprotonation. So step 3 is called a deprotonation. The D means to take a proton away. What is the overall mechanism of this reaction? You get a carbocation. That is an SN1. You've substituted the bromine for an OCH3. So this is an SN1. Okay, number 14. The net reaction for 13 is here. What did you make? You made an ether, okay? This is an ether. So you started with a methyl alcohol and an alkyl halide, and you made an ether. In general, an alkyl halide is classified as an electrophile because the leading group leaves to give a carbocation. In general, an alcohol is classified as a nucleophile because it's donating the electron pair. Once your group has reached an agreement, come up with a plan for determining the role of an alcohol in the above reaction. The alcohol acts as a nucleophile in this reaction. Okay, so now you have your additional problems, and you're going to find out you need to draw your electron arrows. Make sure you get formal charges in there. I will take off half a point. I need all structures, and you're going to find out if alcohol acts as a nucleophile or an electrophile in some of these reactions. So your problems are on page 184 and 185.